All right, what makes this second example in the 3-minute review today here, folks, strange isn't because it's an application one like the first one. This is a reciprocal trig function. So, I mean, I'm hoping your instincts are to like not deal with this at all, but to change it into something that's more familiar. More familiar would be the related, um, the related it's reciprocal, and so something that's more familiar to us. So how do we actually deal with the sign on the bottom? Well, I'm gonna, rearrange this so it's not so awful. Okay, and watch what I can do here. Can I do this? Am I allowed? Well, as long as I'm not multiplying by zero, right? Multiplying or dividing by zero, and I also know the cosecant is undefined for a bunch of values whenever sine 4x is zero. So I'll state those restrictions, and we'll notice that, make sure that we'll keep our eyes out, nervous eyes out for when sine 4x is equal to zero. That can't happen. And now notice, what have we done? Well, we changed something that looks unfamiliar into something that should look quite familiar. We realize that the 4x in there is kind of a pain in the butt, but it's not bad either, and we'll get into this in a second. First of all, have a little bit of a think here. Um, we know that this would have two solutions from 0 to 2 pi, and this should be from 0 to 2 pi. Um, so how many solutions is this going to have? This has two. This has, because it's a horizontal compression factor 4, the period is 2 pi divided by 4. How many solutions I should have 8 solutions. And that I already think about even at this stage. Well, how do I solve these ones with the period changes? I'm going to solve a simpler problem. I'm going to solve sine theta equals a half, right? Where theta is equal to 4x. And this is a trick we've pulled a couple times now, so no one should be scared. Don't be scared now, even though we're kind of scared of the bottom being 0, but we're not scared of this theta business anymore. Where are we here? I want to draw a diagram. That's the first step, right? Diagram, calculator, think. Now, of course, this one's not a diagram one. This is a special angle, right? So from the chart, we get the ra is, when sine is a half, the ra is pi over 6, right? Pi over 6. And so I know where I get the sine as a half, by the way. If I wanted to, I could think of the y-coordinate being a half, and I could get my diagram that way. But it is a special angle, and I know that the sine is positive in this quadrant and this quadrant. We know 100 ways to think of this correctly to get um, the right diagram. So there's theta 1. Here's theta 2. And now we're off to the races. We got theta 1 is equal to, well, it's just equal to pi over 6, right? Pi over 6 is the related acute angle. No plus or minus from pi, but I will write in my general solution here, right? And now I can start thinking about, well, solving for x. This is for x1. And I can't see where my 8 solutions are going to come from. This looks like just one, but we'll think about that in a second. Divide each part by 4, right? So now I got pi over 6 divided by 4, or I could write it like that, but that looks terrible, so that's why I wrote the other way. How do I divide by 4? Well, I flip and multiply, and in fact, the 4 ends up in the bottom. That's pi over 24. Pi over 24. And I divide this by 4, I get 2 pi divided by 4. This is actually pi over 2, right? And that's the period. We kind of knew that, pi over 2. 2 pi over 4, where the period was. And then I can start thinking about my general solutions. I will soon. I want to get my sort of specific solutions. I'll get them soon, but I want to think of my other general solutions first. So I'm going to go with theta 2 over here, which is almost half a turn pi, except for the related acute angle, pi over 6. And then my general solution. Are you getting good at doing this in your head? Pi is the same as 6 pi over 6, and then a lot of people are getting used to just writing down the 5 pi over 6. And now, though, theta 2, remember, was 4x. And so I'm going to write 4x2, divide by 4. I'm not going to scare anybody, I hope, by just writing this is 5 pi over 24 plus pi over 2n. And my general solutions, I'm just going to copy them here. The solution set is pi over 24 plus pi over 2n, and then this one, the second solution, 5 pi over 24 plus pi over 2n. And now where are my specific solutions? Remember, I want to go 0 to 2 pi, so certainly this first one. And then I got to start adding pi over 2's. For n equals 1, I'm adding pi over 2, or I'm adding with a common denominator. Here, let me do the whole calculation, then we'll get a pattern going, I hope. For n equals 1, I'm going to have pi over 24 plus pi over 2, n is 1. And then common denominator, I'm adding 12 pi over 2, right? That's pi over 2, but written with common denominator 24. So 1 plus 12 is 13 pi over 24. And then for n equals 2, rough work, I've got pi over 2 times 2. Again, I could cancel this, but I need to get a common denominator anyway. This is plus another 12 pi over 2, or 24 pi over 24. And so this is 25. And notice, what am I doing here? I'm just adding 12 pi on the top, which is pi over 2 when the bottom is 24. Adding 12, adding 12, adding 12, adding 12, adding 12. When do I stop? Adding 12, I don't know. Yes, I do know. I stop when I get to 2 pi, right? I want to get to 2 pi. Well, what's 2 pi in terms of 24s? 2 pi, and this is again in the margin here, I guess, 2 pi over 1 is equal to what over 24? That's 48 pi. So I stop at 48. That one's too big. And there are my 4 solutions. Makes sense. 4 solutions that go with that first principal solution. And now I'm going to list the next. 5 pi over 24. And then I'm going to add another 12. It's still just 12 pi over 24. Add 12 is 17 pi over 24. Add 12, 29 pi over 24. Looking for my cutoff of 48. Add 12 pi over 24 is 41 pi over 24. That's my 8 solutions, but I'm going to try again anyway. Add another 12 is 53 pi over 24, which is too big. And I'm done. 1, 2, 3, 4, 5, 6, 7, 8 solutions. Lovely. Lovely. Wow, 8 solutions just between 0 and 2 pi. Phew. Okay, the homework has some of that. Okay, there are a few like that, and oops, it's all coming apart on me here. Can I put it back together? And it says, hopefully we'll have time to start some review. I don't know, not with this activity. And here's the activity. I will give you some slips of paper. On these slips of paper, this is the, hopefully you got these instructions in front of you. This is for the in-class activity. You will have a bunch of algebra equations and a bunch of trig equations. And then on a piece of paper, you write the algebra equation on the left, the corresponding trig equation on the right, and then you solve the algebra equation. Then you solve the trig equation. Let me give you a for instance, a quick for instance here. So here's all my slips of paper, right? There's slips of paper all over the place. And you want to match them up. Which ones kind of look, this is an algebra equation, this is a trig equation. They don't look the same, right? This one kind of looks like this one, maybe because there's a 2 in it, but there's no 3 in it over here. Let's try and match them up. See, this one is an algebra equation, and it's x times blah equals x. X times blah equals x. All right, so then there's an example. I have my trig equation, or that's not here. Let's move this over. Yeah, good. That is my trig equation. Here's my algebra equation. Right? And you're writing them down. You're not writing on my little slips of paper, my little cards. And the idea is I'm going to solve this. Well, we haven't seen many that look like this, but I can still solve it. You might be tempted to cancel out x, but you can't because you might be dividing by 0. And in fact, that's one of the solutions. What the better thing is to do, because the hint was to factor, is to move this over to the other side. And now we've got a common factor of x. Now I've got two brackets equal to 0. What do I have? Well, two brackets, I guess one thing. X equals 0 or y minus 1 equals 0 or y equals 1. Therefore, the solution set equals x equals 0, y equals 1. They're done. But how does this fit in with my trig equation? Well, it's the same thing. I can't just cancel. I'm going to move the cotangent over to this side equal to 0, and then I'm going to factor out the common factor of cotangent. In the brackets, I have cos x minus 1. And then here, I get two equations. I get cotan x equals 0 or cos x minus 1 equals 0. Two trig equations. Two trig equations. And now how do I solve this? Well, I might think of a graph for this one, right? What does the cotangent graph look like? Do you remember? Well, you should remember because the test is coming up soon. Soon enough. This is pi. This is pi over 2. And this is only one way, by the way. You might think of, okay, the cotangent to 0 is when tan of x is undefined, and maybe you get it that way. Okay, this is one of the special cases, though, and certainly between 0 and 2 pi, I've got two solutions here. I have x equals pi over 2 and x equals 3 pi over 2. And that's from this one. Well, what about from over here? When is cos x equal 1? Now, how am I going to solve that? I might get rid of this card first, but I might think of a graph. Right? I could think of the graph of y equals cos x. When is it equal to 1? Bing, bing, I get my solutions. Another way to get this solution is, I think of the x-coordinate. When is the x-coordinate 1? The x-coordinate is 1 only at 0 and 2 pi. So x equals 0, x equals 2 pi. And notice that these are all just principal solutions. I could think of the general solutions by adding 2 pi n to each of these. Putting it all together, even though it's getting to be a mess here, the solution set to the trig equation is pi over 2. 3 pi over 2 went with the first one, and with the second one, I got 0 and 2 pi. All right, this is actually a quadratic trig equation, and I want you to try some, as many as you can, in class on your own, on top of the linear trig equation exercises. Whew. Okay, that's it. The end is near, folks.